Okay, welcome to Level 1 Science Online with Henny van Vuren.
Okay, hi Year 11s. You gotta love it when you record for 7 to 8 minutes and then you realize that you didn't turn the microphone on. Haha. Anyways, so here we go again, even though you weren't here for the first one. So in the last lesson we came all the way to Punnett squares and we talked about something that is homozygous recessive, heterozygous, or homozygous dominant. Okay, and we looked at how we can predict the potential for this fertilization to produce a individual that might be a black rabbit, or in this case an agouti rabbit. Okay, and we use a Punnett square for that. So we looked at this and we started to look at genotype and phenotype ratios. So a genotype ratio is the number of different genotypes. Remember, that's the combination of either a big R and a little r, or a big R and a big R and a little r and a little r. That's your genotype. Whereas your phenotype ratio is the physical feature. Remember that? Physical feature. So in this case, the rabbit with straight ears, that is a dominant trait. So if that's a dominant trait, and we have two straight-eared rabbits, because these are two heterozygous dominants, and the moment a dominant is there, the phenotype will be seen. Okay, so as you can see here, these two cross with each other. In the first one, and another big R, and that is a homozygous dominant, because that R comes across and that one. Now this R goes one down, and we have a big R and a little r. Okay, so that's going to be a heterozygote, but he's got a dominant trait, so consequently his phenotype will be straight-eared. And then this one goes across, big R, little r, and again you have a heterozygote, so your phenotype that you'll see is straight-eared, and over here we have little r, and at last we have a recessive phenotype. Okay, and recessive phenotype in this case is lop ears. But can you see your genotype ratio is 1 homozygous dominant to 2 heterozygotes to 1 homozygous recessive. Whereas over here we have 3 straight-eared rabbit to 1 lop-eared rabbit. And that's your phenotype ratio. The same thing over here, your genotype ratio is going to be 1 homozygous dominant to 2 heterozygotes to 1 homozygous recessive. But your phenotype ratio is going to be 3 purples to 1 white flower. Okay, I hope you guys understand that. Now, when you see the recessive trait, the moment you see the recessive trait, you have to know that it is always going to be a homozygous recessive. Because if the dominant trait is present, the plant will be purple, or you will see the dominant trait. But if you have 2 recessive genes, or 2 recessive alleles, then immediately the plant comes up as the recessive phenotype. So if you know this, then you can always say, okay, that individual there, that organism, has the recessive phenotype. It looks, the physical feature is recessive. So consequently, we know that its genotype is going to be homozygous recessive. In other words, little p, little p. Now that is very, very important, especially for breeders. People who want to breed and really make sure that they, for instance, breeding budgies or breeding racehorses or any of that. So I think I told you guys I recently bought a budgie for my son because his other budgie died, and its feather color is called a harlequin, and the harlequin is a known recessive. So we can see that it's a harlequin, therefore we know that it is homozygous recessive. And that homozygous recessive is going to be little h, little h. or maybe little p, depends on what you want to say. So by looking at something and seeing the recessive phenotype, you immediately know what the genotype is. Now breeders use this to do what is called a test cross. Okay, a test cross to see if something is purebred. Purebred simply means you are homozygous. Now, when you're homozygous recessive, that's easy, we can see that. But how do you know if the purple plant is homozygous dominant or heterozygous? You all understand that? How do we know if this purple plant is a purebred organism? Well, we cross it with a known recessive. So if we take a purple plant that can either be big B, or it can be big P, little p, and we cross it with a known recessive that is going to be homozygous recessive, I can only give a little p. Then we have two Punnett squares. You can see this is the big P. Big P can only give a big P, and in both cases, and there. And the little p can only give little p's. So when you look at the offspring, you will notice that every single one of them is going to be heterozygous. So in the phenotype, which is the one that we can see, we know that every single one of it is going to be purple. And if you do this for enough times, because you can't just say after the first time, because remember, this is every fertilization. So if the individual over here was a heterozygote, it has a 50-50 chance of producing white offspring for every fertilization. So if you cross these guys multiple times, you might end up seeing a white flower come through. And the moment you see that recessive trait, you know that this one is not a purebred. But if it continues to be just purple all the time, even after several breedings, then you know that this is most likely a homozygous dominant purebred organism. You cannot for certain say, because remember, every time a sperm and an egg comes together, these are the chances, 50-50. So even if you flip a coin for 100 times, and 99 times it is on heads, the next time you flip it, your chances are still 50%, because it's a 50-50. So that's why you need to always continue to monitor the offspring. Okay. That is a test cross. Again, guys, very, very important. So a test cross is used to determine the genotype of an unknown individual that displays the dominant phenotype. The individual is crossed with a known homozygous recessive. So in this case, we see a gecko, and the gecko is green, and that is the dominant phenotype. And we see on top of a red albino type gecko, and we know that is a recessive. So if it is a homozygous dominant, you have a homozygous dominant and a homozygous recessive, you will always get heterozygotes. Always. Okay? Which means the heterozygote's always going to display the dominant trait. But you need to continue to monitor this over time, because there is a chance that you have a heterozygote, which in this case is going to be big R, little r, and you have a 50-50% chance. Can you see there? There's a 2-to-2 or a 1-to-1 ratio, which makes it a 50% chance of them being either albino or green. And if you see any albinos pop up, you immediately know that your dominant trait is not homozygous dominant, but it is heterozygous dominant. Okay, very important, guys. Test crosses. So, determine the genotypes of the parents of whatever is given in the problem. Set up your Punnett squares. This is how to actually answer the questions, but we've gone through that already. Okay, a heterozygous male, black-eyed mouse is crossed with a red-eyed female mouse. Heterozygous male, black-eyed. So black must be the dominant trait. Okay. Crossed with a red-eyed female. Predict the possible outspring. So heterozygous, we know it's going to be one big B, one little b. And the red-eyed one is because it is recessive, we know that it's going to be little b, little b. And consequently, when you do your Punnett square, when making the egg and sperm, in this case the male is making can only give okay, so the male, as you can see there, can give a big B there, and the female can always only give a little b. So you're going to have a 50-50% chance of having a red-eyed mouse being produced, or a 1-to-1 ratio. Same thing for a pea pod. So it's just repeating the same thing. Now you have two heterozygotes, smooth and wrinkled. There are two alleles for pea pod, smooth and wrinkled. Predict the offspring from this cross. Two heterozygotes are crossed. There are two. Smooth must be dominant, as the phenotype smooth plant is heterozygous as both. Okay, so they are both smooth. Because they're heterozygous, we know that smooth has to be dominant. Does that make sense? If you're heterozygous, you have one of each, a dominant and a recessive. And if they tell you they are heterozygous and they are smooth, then you know that the dominant trait is smooth. Alright, so dominant trait is smooth, and they are heterozygotes, so we cross them together, and we will have a 1-to-2-to-1 ratio of genotype ratio, but our phenotype ratio is going to be 1-to-3 for smooth. So 3 smooths and 1 wrinkled. Okay, I hope that makes sense. Genotype ratio 1-to-2-to-1. Phenotype ratio 3-to-1. And you have to write 3 smooth to 1 wrinkled. If you don't have the wrinkled or the smooth word there, you cannot get excellence. Now I'll look at the kiddies. Okay, parents' genotype can be predicted by the phenotype of the offspring. So if you know what the phenotype is of the offspring, you can figure out what the parents' genotypes are, or predict. If 100 of the offspring show the dominant phenotype, then at least one of the parents is most likely homozygous dominant. If any of the offspring shows the recessive phenotype, then each parent must contain at least one recessive allele each in order to have offspring that has recessive alleles. If parents show dominant phenotype, then they must be heterozygous. We talked about this with the brown eyes and the blue eyes. Okay, so if your parents both have brown eyes and you have blue eyes, then it means that the only way that you can have blue eyes, which is homozygous, recessive, or little b, is that both your parents are going to be big B, little b, or heterozygous, because one of them had to give you a little b, and the other one had to give you a little b. Okay, so this is what this slide basically tells us. So, to do that, we can then look at pedigree charts. This is really fun. It's kind of like solving puzzles, okay? So, and it'll always give you a key. A key is something that will basically tell you what means what. So your affected individual is going to be colored in, whether it's male or female. Those are twins, that is a child, and that is when they are mated. Okay, so it's not always humans, so, but as you can see here, this is a heterozygote and another heterozygote, male and female. They have kids. one there, and one there. Now in this case, the mom or the dad could have given a dominant A allele, and the mom or the dad could have given a recessive A allele. But none of these, let's say this is for, I don't know, blue eyes, because it's bluish turquoise, this individual will not have that. This individual is going to have the dominant trait, which is going to be the brown eyes. But this individual over here is homozygous recessive because both mom and dad gave a little a. Now, we look at these, and this female, which is not affected, is mated with a male that is not affected. Okay? But lo and behold, they again have a recessive child. And if they have a recessive child, it means that they had to give the little a's. But do we know if this one is homozygous or heterozygous dominant? Because this one can give a big A, and this one can give a big A, and that would mean that they are unaffected. So can you see that we cannot work out the genotype of that one? Over here, this individual is affected, which means they can only give a little a. So one of them has to be a little a. But this individual can be homozygous dominant, meaning big A, but he can only give a big A, and hence you will have a unaffected child. But if this guy was heterozygous, in other words big A, little a, it can still give a big A and have this. That's why we don't know what that one is. But it's really fun. It's a little bit like solving a puzzle. Okay, so lop-eared versus non-lop-eared. Okay, so when an individual has recessive phenotype, the pedigree chart, then the genotype must always be homozygous recessive. Okay, so we know this. Lop-eared, the moment you see one, it's going to be little r, little r. Now, look at these two. We want to figure out, is he homozygous dominant or heterozygous? So if we cross him with a lop-eared, he's going to give a big R to have a straight-eared child. But look here, he actually had a lop-eared child. Where did that two recessive R's come from? One had to come from this individual, which means this individual has to be a heterozygote. Okay, and then here's a new mating that takes place. Two straight-eared. Okay, but we know that her mom could only give her a little a. And we know that the dad gave a big R. Sorry, R. So we know that she is a heterozygote. And then this guy, we don't know, because all three of the babies have straight-eared. Which means, even if this was a heterozygote, because there's a chance that you can always give the big R, one of them, because they both have big R's in them, the other one can still give a little r. We don't know the genotype of these, and we don't know the genotype of that guy. Alright, but over here we know mom gave a little a, dad gave a big A. We know that's a heterozygote. We mate it with a lop-eared, which is, we see the phenotype, we know it's little r. Therefore, they can have a child, and the child is lop-eared. That proves to us that this one is a heterozygote. But in these two cases, this rabbit gave the big R, because this one can only give a little r. Does that make sense? We'll do a few exercises, don't worry. I've showed you this before. This is Queen Victoria. She was born with something called hemophilia. So all the males that have it is going to be orange, and all the females that carry it is going to be in white. But a normal female doesn't have it, and she doesn't carry it. So Queen Victoria was a carrier, but the mutation started with her. And from there, it went down, and Alice got it, she married somebody, and then Frederick William had it, and he died at 3. Irene was a carrier. She married Henry of Prussia. Prussia in those days was called Germany. No, in these days are called Germany. And they had children, and Valdemar of Prussia, he lived until he was 56, but he was a hemophiliac. Henry, he died at age 4 because of that gene that came all the way down to here. Over here we have Alice and whoever this was. Another child was Alexandra, and Alexandra, they had a child called Tsarevich Alexis, Tsar Alexis, and he was murdered. And I think, if I'm not mistaken, that down here, these are the Russians, and you have Anastasia and so forth during the Russian Revolution. Okay, so this is a Viscount. I think Viscounts are from France or Italy, I'm not sure. But you can see there, Leopold Maurice. So because of her gene, it spread through a lot of the royal families in Europe. Okay. Alrighty. Now, sex determination, gender determination, is, I've talked about this before. We said when you have the female, because she is XX, she can only give an X. Okay, it's almost like being homozygous female, whereas men are always heterozygous. Okay, it doesn't really work that way because it's a whole chromosome. But females can only give an X chromosome, whereas males can give an X chromosome and a Y chromosome. And if the Y chromosome wins the race, gets to the egg first, we have a boy. And if the X sperm gets to the egg first, we have a girl. So the gender of the child is always determined by which sperm actually arrives at the egg, because the egg will always have an X chromosome. But the Y chromosome can either be a Y chromosome sperm cell, or it can be an X chromosome sperm cell. Okay, and therefore, whenever there is a fertilization, you have a 50-50 chance of having a boy or a girl. Always. If it's natural fertilization, it is a 50-50% chance. Okay. This was in 2013. Question, Huntington disease. And Huntington disease is a genetic disorder in humans. It is caused by a dominant allele. The normal allele is homozygous recessive, or is recessive. Just want to quickly jump out of that and then jump back in, because I need my controls. Okay. So, the normal allele is recessive. So, Huntington's, affected male, affected female. So, using H and H, give the two possible genotypes for an individual who has Huntington's disease. So, it's caused by a dominant allele. So, that means that Huntington's can be homozygous. I cannot write with a mouse, it's terrible. Anyways, homozygous dominant, or it can be homozygous recessive. Bang. And just like that, you have an achieved point. Easy peasy. Now, state the genotype of individual 9 in the pedigree chart above. Individual 9 is unaffected. Unaffected. If you are unaffected, and the normal unaffected gene is recessive HH, it has to be little h. Little h. Okay? Because it is the recessive trait. Question 1c. State the genotype of individual 10 in the pedigree chart above. Now, if you look at this, let's look at the mom and dad. That guy is little h, little h. Okay? Because it's an unaffected female. This one has to have one big H. But can you see, they had kids. This guy was affected, so he had a big H. And we know the mom could only give a little h. This guy, remember this is a new marriage, or a new, yes, it's human, so a new mate. this one was unaffected, and unaffected has to be little h, little h. So the mom gave her little h, but it means that the dad had to give a little h, which means that has to be a little h. And then this guy was affected, so the dad gave his dominant, and the mom could only give a little h. And then this child was unaffected, and unaffected we know is little h, little h. So, coming back to number 10. Mom can only give a little h. Agree? And dad can either give a big or a little, but because the child is affected and it is a dominant disorder, the dad had to give a big H. Voila, there's the answer. But we can take this one further, because I like doing this. So over here, we know that it is we've already worked out that the mom had to give a little h there, so we know that's a heterozygote. So, for all of them that are affected, they couldn't get it from the dad, because the dad can only have little h's. So there's a big H, there's a big H, and there's a big H. And we know that when it's the recessive trait, we can put the little h's immediately. And now this guy is donating a little h to everybody. So heterozygote, heterozygote, heterozygote. Ha! Now, can you see this guy is also not affected, so he's a heterozygote. So all of these guys will be heterozygotes. Homozygous recessive, what am I saying? Homozygous recessive, homozygous recessive. They can only give little h's. So all of them will be little h's. But over here we have a homozygous recessive. One child has the disease, which means it's a cap. There's a dominant allele from the dad. And because they had a normal child, we know the dad had to be heterozygous. So, looking at that, that heterozygote allele came back, all the way back from his mom. And now that heterozygote allele is over here with the grandchild. Okay, I hope that makes sense. Okay, I think we answered all of this already. Okay, the allele for brown eyes B is dominant. I actually think we should call it quits here today, and then you guys do a few pedigree charts in the iPad for me. I will put those pages on the OLE. Okay, guys, thank you very much, and thank you for your hard work. I hope that you guys are doing well. Okay, please look on the OLE for which iPad pages you need to do. Have a great day. Bye.